La la la. All right, Dr. Smith, right back at you with some more free body diagram problems. So now we're getting to ramps. This is where things can get kind of tricky sometimes. So, and this is a really good place to be using. Hold on, let me close this old thing. There we go. A really good place to be using using the idea of rotating your coordinate frame. So I'm going to demonstrate how to do that. So let's do this problem here, where you've got no friction. You just got a block sitting on this sloped surface with a slope of theta. Okay, so here I'm going to redraw I'm going to sketch the problem here. Wow, that's horrible. Let's try that again. There we go. And that's still horrible. But anyway, there's our, let's try to put that in. There's our slope theta. Wow, oh, come on. Try a little harder, Smith. All right, there we go. There's our block with mass M. We have no friction. No friction. And we have, I think that's it, right? So, first let's pick some coordinate axes. Now, we could do this with your standard, horizontal, vertical, but it's actually easier if we set them up with the forces, or with the axes going along the slope and perpendicular to it. So, I'm going to do let's do, right, gravity goes down that way. That's G. So, we can just sketch in the forces here. There's this weight here, and then the normal force. Which way does the normal force act here? Well, I'll give you a hint. It doesn't act straight up, because straight up is not perpendicular to the surface. Normal force always acts perpendicular to the surface of contact. So there is your normal force. So weight goes down, normal force goes this way. And now that I've made this thing thoroughly legible, hopefully you remember what I said. Let's do our free body diagram. So we're going to FBD for the block. There we go. All right. And first we want to draw in, well, I'll tell you what, let's start with our point for the block. Then we're going to draw in our coordinate frame. I'm going to do this carefully here. Gee, I keep hitting that stupid button. All right. So there's Y and X. And if we do a tilted coordinate frame, we need to show what angle it's making with the horizontal, or with the right angles. So in this case, I'm going to do it by showing theta as our angle between the horizontal and the x-axis. So now we've got this thing set up. There's our dot. Probably drew it a little too close to the axes, so I'll erase it and do a new one. So there we go. What are our forces? Well, there's our normal force acting like that, right? And there's our mg acting like that. Actually, let's do weight equals mg acting like that. And we can show that the angle between these two, well, actually, the way we want to show this is anything that sort of looks like it's parallel to one of your axes can be assumed to be parallel. What's not parallel is weight. So there we go. So let's go one more step now. Now we've just shown where this is. These are all our forces acting on this object. So let's go one more step and go ahead and draw the object. And we're going to break everything down to components. There's your normal force. That's already along the y-axis, so we don't need to componentize that. Remember, you're turning everything into components that go along x and y. Normal force is entirely along y, so we just copy that over. And then for the weight, we have that component is going to be the magnitude of the weight times times cosine of theta, right? So this is going to be mg cosine theta right here. And then the other component is going to be that way. See, it goes like that. Mg sine theta. Okay, so there we are. Now we can write our equations of motion very simply. So we can say sum of forces in the x direction, so x is on this way, is mg sine theta. And what does it equal? Well, I don't think we were actually told whether this puppy is accelerating or not. So let's see. Yeah, they didn't tell us anything about that. So we can just we can say, well, look, this is obviously not going to be 0, right? Unless sine theta is 0, but that's kind of boring. Otherwise, why'd you draw the slope if theta was 0, right? So gravity isn't 0, mass isn't 0. If the mass is 0, why are we doing the problem at all? There's no object there. Who cares what happens to nothing, right? So this is clearly going to be accelerating. So we should put in MA. Let me find out what it is. In fact, literally you can take that and find out what it is in just a second. But anyway, and then the force is in the y direction. We have this mg. No, hold on, we don't. Okay, so the first force we have in the y direction is the normal force going up, so that's positive. And then we do minus this force going this way, minus mg cosine theta. And that's going to equal 0 because it is not accelerating in the y direction. It's staying on the slope. So from this, I mean, if we wanted to find stuff out from this, this is done with what we were asked to do. If we wanted to find stuff out from this, we could say that, you know, the normal force equals, it's just going to be equal. It has to be equal to this for this to equal 0, right? So normal force equals mg cosine theta. And then over here we can say, well, these two have to be equal, right? And you can cancel the m's out. So from this, we can say acceleration of the block is going to equal g times sine of theta. And this is actually kind of an important result. So, you know, first of all, what we're saying here intuitively is that if you have a slope and you put a block on the slope, or any object on the slope, and there's no friction, the object's going to start rolling down the slope. I mean, you know, there it is. And the steeper your slope, the greater your angle theta, right? Which means the greater sine theta is, right? So the steeper the slope, the faster the object is going to accelerate. So this is a very intuitive, real-world, you know, result. You know, you have something on a gentle slope, it'll start going do, provided there's, you know, no friction. If you have a very steep slope, then it's going to go, you know, just rocket down that slope. And Galileo took advantage of this actually back when he was doing his experiments. All that stuff, you know, people talk about Galileo dropping balls and seeing how long it took them. What he really did for most of it was use slopes. And that way, you can take something that's going to take a long, you know, going to happen really fast. If you drop a ball, it goes pretty fast, right? But you can slow down the whole falling procedure by just having, instead of dropping, have a ball roll down the slope and just see how it behaves there. So anyway, that's basically the result we get here. This here is the useful answer to get out of that. So next I'm going to do sort of a much more complicated version of this. So come back for that in a second.